All right, we're going to take a look at two different vector applications using the operations that we've learned in previous units. Before we start with the applications, we want to break down how to write a vector given its magnitude and direction. So our magnitude, if we look at the vector given here, we can break this down into A and B as our horizontal and vertical components because we're going from 0, 0 to AB, or the point AB. So the magnitude would be the square root of a squared plus b squared, which we may need to do some calculations. And then we're also going to do tangent theta is equal to b over a, and we're going to solve for theta in the appropriate quadrant. This may actually look pretty familiar. Hopefully it does a little bit. We did the same thing when we looked at polar coordinates, and we converted back and forth between those. Because a polar coordinate, if you think about it, has some similarities to a vector. You're given a radius, which is a distance, and a direction in the theta measurement. So essentially is a vector, but we're just not graphing these vectors in a polar coordinate system right now. So then for A is going to be the magnitude of u times cosine, because it's our x value. So again, thinking back to polar coordinates and also our unit circle. And then the magnitude of u times sine would be our y coordinate. Cosine goes with x, sine goes with y. And if we want the full vector is going to be the magnitude times each of those components. So and sometimes that magnitude will be factored out, but a lot of times we want to write the vector in that format because it's going to give us the two different pieces that we need when we're doing our vector calculations. So again, just put on the side similar to polar. Now we're doing the magnitude of u, or that distance, instead of the radius. So our cosine theta, our sine theta were the 2 points that we had used prior. R is now getting replaced with this symbol for magnitude. All right, so we're going to need that when we are breaking down our first scenario. It's going to be a dot product application, and it's for work. Most likely already have done this or will do this in physics as well. And although the formulas might look different at first, you'll see some similarities. Work is the dot product of the vector and the force applied to it. So the first thing that we have to do when we're looking at this is break things down into our different vector components. So we'll draw a little sketch in a rectangular coordinate format. Take a look at our scenario. A girl pulls a wagon with a force of 50 pounds. How much work is done in moving the wagon 100 feet if the handle makes an angle of 30 degrees with the ground? So if we draw what's happening in this situation, we're making an angle of 30 degrees with the ground. We're going to start at a position of 0, 0. We'll call that point A. We want to move the wagon to point B 100 feet across the floor. We'll call that 100, 0. So we're looking at vector AB. And she's pulling at a force of 50 pounds. So that's going to go here. If we want to look at creating a vector for AB, that's easy. Since it's just horizontal movement, we're doing 100I plus 0j. Where we will need to use the information from up above is for the force vector, because the force vector now has an angle. So our force vector is going to be 50 cosine 30 I plus 50 sine 30 j. Once we have those two things created, I mean, we can even simplify this down. I'm going to do both, since we can do this in exact format, just to refresh some of our exact values. This would be 50 root 3 over 2 times I plus 50 times 1/2, or 25 root 3 plus 25j. Now, if this is an angle that's like 33 degrees, which we don't know an exact value for, you don't really need that because you're going to be multiplying, and you most likely will be able to round to a certain decimal place. So if you want to do the work application for this, we're doing the force vector and the dot product of that with AB. And this is where it's now going to look more like what you probably did in physics. If you think about it, part of this first vector has a 0. So I'm doing 100 times 25 root 3 plus the 0 times 25. I did that slightly out of order, but that's okay. This part is 0. So really what you're doing is the 100 times 50 cosine 30. When you're moving something horizontally, most likely the formula that you're using in physics has that cosine in it, and you plug it in all in one shot. So we would either get in exact format 2500 root 3 foot-pounds, because we are not in the Newton meter option for joules. And then if we rounded this and multiplied by the root 3, we would get 4,330.13 foot-pounds. So just make sure you pay attention, if it's either Newton meters or foot-pounds, to put the right units with that. And I'm going to go a little bit further in this video before we do our second application, which takes a little bit longer. And this is actually just using plain addition and subtraction in our applications. I'm going to talk about direction angles and how to use those to come up with something similar to our force vector from up above. So we are going to go back, I'm just going to scroll back a little bit to setting up the vector with magnitude and direction. We just need to have the direction in the right format. So to do that, we're going to look at a couple quick examples. Notice I have 3 sets of directions, north, south, east, west. And we're going to talk about what it means to say north and then 30 degrees east. This means start at north and go 30 degrees towards east. So the 30 degrees would be in here. So we're either going to start north or south and then go towards the east or west. I don't want to use that angle when I'm coming up with a vector. I want the standard angle. So you're going to be using 90, 180, 270. Actually, most likely 90 and 270, because we're going to be doing just north and south. And either adding or subtracting from those. So in this case, I want to do 90 minus 30 to get the angle that I'm going to highlight in red. That's going to be my standard angle, because that initial format for our vector assumes we're using a standard angle. So before we even do anything, we always want to switch to a standard angle. So we're just going to do 2 more examples of standard angles. The next one tells us to start at north. So we're starting at 90 degrees, and we're going to go towards west 55 degrees. So from there, we're going 55 degrees. The angle that I want for my standard angle has to start on the positive x-axis and go all the way to there. So what you'll notice is, since we're going past 90 instead of subtracting, you're going to add the 55 to 90 to get our standard angle of 145. And then our last example of converting into a standard angle, we are going to start at south. The degree measure for south is 270, so we're starting there. And then we're going towards east. So we're starting at south, we're going to go towards east, 35 degrees. Again, what I really want when I'm talking about my standard angle is the entire angle that I highlighted there in red. So since we're going past the 270 degrees towards the east, we're going to do 270 plus 35 to get our standard angle of 305 for this. And similar to finding a standard angle, we will eventually have to also take standard angles and convert them back into the north, south, east, west notation that you're seeing up here. So we're going to stop the video there, and our second video for the applications will take us through one of those direction angle applications with just plain adding and subtracting, really.